So getting it all together here. All right. So let's see. First thing, an announcement. I was able to find a classroom for the 2 classes that we lose this room due to comps. It's actually the one, let me get my bearings, all the way that way. It's the, what I thought was the Teacher Learner Center, but it's actually the personal development area. It's the big room that they have talks and stuff in with the round tables at the end. It's number 116. So on February 6th, as well as March 26th, we're going to have class and office hours in there, and those days are marked on the online syllabus as well. So that's some good news. Looks like everyone was able to get the homework done. If you look at it and found that you missed some things, let me know and I'll let you fix it. I can go in and manually reset it so that you haven't submitted after all. For future reference, if you ever get your homework done early and then have buyer's remorse, right? You turn it in and then you realize you messed something up after we go back over it in class. Just let me know if you want to change your answers and I can reset it so that you can go back in and change it. I just have to be careful to do it when no one else is currently working in the data set, otherwise things can get overwritten. So, all right. So we have some new stuff to do today. Lecture 1 to start with, and then example 1 is more of an activity, most of which I hope you can do at home. Have you had a chance to look at the online checklist for getting ready to use the virtual desktop? Okay, any problems with that so far for those of you who've tried? No? Okay, if you run into any problems, please don't hesitate to contact me. I can help you try to troubleshoot to whatever extent I can. But this is there. So we have a couple lectures to go over, and then we'll try to actually run some stuff in class, I think maybe next Tuesday based on the timing. It might be Thursday, we'll see. The idea is that software is a necessary evil. This class is not about software. This class is about quantitative data analysis. The hardest part of your first assignment will be figuring this stuff out. The rest of it will be so straightforward you could actually have done it in Excel. And several people last year did that option. Not something I would encourage, because the point is to get used to this kind of software, but that is as a backup. So this part is frustrating at times, but once you figure it out, you'll have it figured out, and then you'll be able to use those skills moving forward.
Yeah, I was going to say on the second page, that's where I kind of...
That's where it went awry? Let me pull this back up again. So which step are you talking about specifically?
Stata.
The stata?
So they said you go and you place some like go on down to step 6.
Step 6, okay. Yes,
yeah,
the path. Yeah, so I will open this up real quick on my thing here. So we have so I'll open both SAS syntax as well as Stata syntax. I have both of these applications installed on my laptop proper, so it runs a little more quickly. It takes some time to boot it up inside the virtual machine. I do not want to check for updates right now. Thank you, Stata. It's very helpful, especially while you're broadcasting and teaching. This wouldn't be the first time that my computer decided to restart itself in the middle of a lecture without my control. That's always fun. By the way, the good news is that these files that I'm opening up, so I'm inside the folder for homework 1, or excuse me, example 1 that I had posted. The files for syntax, the ones that end in .do for Stata or .sas, those are just text files. You can open them in any text editor. You can edit them in any text editor. There's different colors that signifies what things mean that we haven't talked about yet. Those colors won't necessarily appear, but otherwise you can look at them and edit them. So I will point to the part that I'm talking about. This is within the Stata version here. So all this green stuff, this is comments, by the way. These are just instructions or notes. It's this line right here that refers to a path. So step 6 refers to figuring out what to put here instead that tells it where your stuff is. That is literally the hardest part of this entire thing, is getting your computer to communicate. You having troubles with that? Yep, it's non-trivial. In part because of the difference between Windows and Macs. So for instance, I had several students last year who eventually succeeded on the Mac, but it was a little more challenging because of something like this. Note the change in the directions of the slashes halfway through.
Oh.
Exactly. This part precedes it if you are using any place that is not the magical H drive. After this, it would be your personal computer, and this would be if you save something to the desktop, for instance, on a Mac. What it looks like on my computer is this one, where inside the virtual machine is this part, and then I use Dropbox for everything, and so that would be the path to it. The easiest thing is the first one, which is just the H drive, which it understands without further instruction or elaboration. So I've given you several examples of what this would look like. Which one is most optimal depends on your combination of whether it's Windows versus Mac, whether you're using the H drive or not. And so step 6 is just figuring out how to get the right information into this spot. Once you do that, everything else should run perfectly without any further commentary. So that will be our eventual goal when we go over this in class. But if you want to start now, this is what we were talking about. In SAS, tiny little font here, it's the same idea except the syntax is slightly different. It starts with this keyword let and then file save, and then the path follows that. So if you are trying it and you get error messages or otherwise, please let me know. And the idea is to get as many of these steps completed ahead of time so that when we actually try to look at this in class, it goes a little more smoothly, trying to learn based off of my mistakes from last time. Or what happened last time, we'll just call it that. So, okay, so yes, getting through through step 5 would be ideal. Then the rest of it should go a little more smoothly. All right, other questions, comments? Did you bring your coffee this time? See, I have a baby bottle of Diet Mountain Dew. Due to a miscommunication, the typical text messages back and forth, you need anything from the store. Yes, I need small bottles of Mountain Dew is what I said, meaning not 2 liters, but bottles I could take with me to teach, and then I got what appears to be a baby bottle here. You know, because that's what your children need, right? When they can't consume all of the soda at once, they need a miniature version. They have baby cans at the store now, too. Have you seen those? They're like this big. They're very cute and useless. Anywho, do you want to talk about lecture 1?
Sure.
We're here, right?
Well, let's do this.
I mean, whether you want to or not, right? We're here. You've made the commitment. You've put on clothes. You've shown up. You've chosen to attend to this over anything else that you could do. So let's make the most of it. So show of hands, how many of you have had some sort of intro statistics course before? Almost everybody. Okay. So that means that basically weeks 2 through 7 are going to be things that you've seen before, most likely. The rest of it may be new. If you look at the content for the second half of the course and you think that a course you have taken in the past covers that material, please let me know and send me the syllabus for whatever course that is, because I'm happy to waive prerequisites if this is stuff that you've seen before. I can almost guarantee, unless you've taken more advanced modeling courses, you won't have seen the second half from the way that I'm teaching it that allows you to build on this course. So the second half will be something new, probably even if you've taken stats before. But this part will probably be somewhat familiar. So there's 2 ways to look at going over material that you've seen before, right? One is, I've seen this before, it's a waste of time. And the other is, wow, I actually know this. I feel smart for a change. Right? Imposter syndrome is real. So we can relish in the one opportunity that we have to feel like we're actually in control for once. I hate to tell you this, but imposter syndrome never goes away. It just changes what it's about. It just changes levels, but it's the same feeling of being less than or not worthy, or that you're somehow getting away with something. It's a way of life in academia. So with that being said, how about we start lecture 1 here, one variable at a time. So first off, what do we need to know about variables? We'll talk about how variables follow functions, probability distribution functions, and then how to grab the salient information by which we can describe one variable at a time. So first off, different types of variables. There's 2 broad categories, right? We talked about this last time. What are they? Feel free to read from your own screens if that's helpful.
Categorical?
That's one, categorical. So in that case, even though the variable might be represented with numbers in a column, those numbers are not numbers, they're words. They're labels of some kind. Specific kinds of that, binary, if you only have 2 categories. Categories that have a natural ordering to them, which is known as ordinal, and then categories that do not have a natural ordering, which is known as nominal. The other overarching kind, besides categorical.
Quantitative.
Yeah, quantitative or not categorical, in which the numbers are numbers. So in that case, kinds of quantitative, the distinctions among these matter far more when the variable is an outcome than when it's a predictor. But we had a couple examples, binomial, rates and proportions, or any kind of variable that has a natural boundary above and below. Counts, which have a natural boundary at 0. You can't have a negative count. And things that are continue-ish, meaning we treat them as if they're continuous and quantitative, even if they don't have intermediate values. For quantitative variables, we need to know 3 things to be able to describe them univariately, to summarize across the cases in a sample. For categorical variables, all we really need to know is how many are in each category. It's straightforward. The frequency in each category divided by the number possible is known as a percent. So for quantitative variables, the one that's a little more tricky, we want to know 3 things. First, central tendency. Think middle of the distribution. And there are 3 main ways that people would indicate this. One is a mean. And note I'm saying arithmetic average because there are other kinds. That's the one that you're used to thinking of. Median is a middle value. That is hardly ever referred to again after this conversation. It will only show up in one other kind of model that I'm aware of. Mode is the most frequent value, and that actually shows up a lot in terms of distributions. Yeah, we'll go out there later. But the other thing that we need to know besides middle of the distribution is how spread out they are. Yeah, so then we get into the idea of dispersion. And the ways that dispersion are operationalized is the main one that's most intuitive and the one that you will find referred to most often, standard deviation. It's how far off, on average, each observation is from the mean. If you take standard deviation and you square it, that gives you variance. So these are the same idea in 2 different metrics. And both of those things will show up in various parts of the story. Standard deviation, I think, is the more intuitive because it's in the metric of the original data, but it's how far off on average is the main idea. For variables in which you have something funky going on, there are extreme values, or it doesn't look like something where just knowing the middle and the width around it is adequate. There's something called interquartile range, which is the distance between the 25th percentile and the 75th percentile. That also will go away after this conversation. That doesn't show up in models anywhere, much like median. Those 2 go together in describing univariate, weird-looking variables. And the third one is skewness, or asymmetry. To what extent is the chunk of the distribution sort of shoved over onto one side versus the other? This is caused in practice by natural boundaries. So for instance, let me get out, so I don't draw on the board since I'm broadcasting and Zooming and all this stuff, but what I do get out is one of my favorite programs. Do you recognize this, anyone? This is Paint.
Yeah.
This is one of the first things I learned how to use when I was like 10 years old. And I still love Paint for basic drawing. I don't have a fancy tablet with a pencil, but I can make pictures. So let's say I'm making a picture like this, right? And this is something like number of cigarettes smoked today, right? There'll be a pile of people that said, that's my best attempt at a pile. None, thank you. And then there's some other distribution after that, right? So this is an example of a skewed distribution. Most of the information is on one side and not the other. And that's a function of the fact that you can't go negative. If you have floor or ceiling effects, like if I drew the distribution for what I hope this class's grades looks like at the end of the semester, I want it to look something like this, or even better, just one big pile right there. Skewed the other way. Most of the information is to the right side. Incidentally, the name for skewness is backwards for how you would think about it. The name for it is the direction that's not where the information is. It's where the tail is. So this is negatively skewed, this one right here, N for negative, and this one is positively skewed. It's backwards from how one would typically think about it. So those are the three things that we would want to know to be able to characterize any sort of quantitative variable: central tendency, dispersion, and skewness. There's actually a fourth that's known as kurtosis. In practice, that is really hard to differentiate from variance, so don't worry about it. It's gone also after today. See, this is how we can get through stuff quickly. I just decide what's important and what's not, and then we don't cover the stuff that's just trivia. So outcomes have distributions, and those distributions are how those three characteristics show up. So the distributions that an outcome has relates to its possible values. So for instance, some variables can't go negative, some variables only have positive values, some variables can go from negative infinity to positive infinity and that kind of thing. So I want to show you just some pictures next. Probability distribution functions. So these are shapes of quantitative variables where they result from a formula. I do not want you to worry about the formulas. I just want to show you some shapes. Because the rest of this semester, we're going to focus on only one shape, the normal distribution, which is coming up here. I just want you to know that there's others out there. That's what I want you to know. Because not everything is normal, as I'm sure you're aware. I steal a lot of my stuff from Wikipedia. So for basic stuff like math, it's pretty trustworthy. For public opinions and things, maybe not so much. But there's a nice list of all the possible probability distributions that people have talked about there. They fall into two categories. There's discrete, so whether or not the values take non-integers. If they don't, it's discrete. If they do, it's continuous. They have slightly different names as a function of that distinction. On all of the pictures that I'm going to show you, the x-axis on the bottom has all the possible values that the variable can take, and the y-axis on the side is how, I'm going to say, likely each value is. When I say likely, think probable. Like, what are the odds of saying this in a sort of a colloquial sense? Just think likelihood in that sense. Likelihood has an actual mathematical definition, but we don't need to worry about that for today. So each of these pictures then shows how that distribution says what the mean should be, what the variance should be, and what the skewness should be. So here's our first one. Simplest case, a binary variable. You can either be pregnant or not pregnant, dead or alive, red or blue. Not political, but like maybe your favorite color or something. You get the idea. There's only two possibilities. So in this case, to be able to summarize a binary variable, you only have to know one thing. You need to know the proportion of people who picked 1 or 0, but one of the two, right? And so these are pictures of 3 different types of variables that vary in how many people picked 1. So for instance, the blue line. If I know that 75% of my sample picked 0, then how much percent had to have picked 1? 25, right? If I know that 50% picked 0, I know 50% picks 1, right? So you only need to know one thing. Said differently, this distribution that characterizes binary variables, it's called Bernoulli. It's capital letters because it's a guy that developed it, named it after himself, as one does in statistics. You'll get to know lots of last names of famous people who name stuff after themselves. You only have to know one thing, the probability of a 1. Once you know that, you know what the probability of a 0 is. Once you know what the probability of a 1 is, the mean, in this case, you also know the variance around it. And something special about this distribution is that the mean dictates what the variance is. So the largest possible spread of information happens when the mean is 0.5. That's when the variance is 0.25, because variance is calculated as the mean times 1 minus the mean. The proportion of 1s times the proportion of 0s. As you move away from an even split, the variability goes down, all the way down to 0 if everybody picked the same answer. So in this case, all we got to know is mean, what follows is variance, and what follows is skewness. That will have implications in trying to represent binary variables either as predictors or as outcomes. Next one, related to binary, is what's known as multinomial, meaning many categories. In this case, you have to know how many categories are total that you have and how many are in all but one of them. So in this case, if I have 3 possible outcomes, and I know that the first outcome has 50% and the second outcome has 35%, I know how much percent has to be in the third. So if there's 3 categories, there's 2 means. If there were 4 categories, can you guess how many means I would need? 3. 5 categories? 4. Yeah. So variance and skewness isn't really a thing. It's just how many fall into each category, where you only need to know all but one. Here's a discrete distribution for a quantitative variable. This is what's known as binomial. This is the number of successes out of the number of possible trials. You might think of that as like proportion correct. That shows up a lot in educational type data. And in this case, all you need to know if your data follow this distribution is the mean. For any given trial, what is the probability of getting a 1? Once you know that, you multiply by the number of trials, and that is your actual mean. So here are 3 different examples. The blue lines show what a distribution would look like according to this formula, which is up here, if you have a proportion likely of getting something correct of only 10%. So most of the people are clustered around here. These people don't have any trials correct. Very few people have any more than 5 trials correct out of 20. So this would be what's known as a floor effect, where you have a bunch of people sort of shoved at the end because they can't go any further. You can't have a negative proportion correct. You can only just have 0. Green here shows the opposite. If the probability of getting any one trial right is 90%, then this would be the expected distribution here, where a lot of people would be expected to have the highest possible, and then even more, sort of only missing 1 or 2. Very few people would be expected to have a score under 15. That's what's known as a ceiling effect. The middle here is if you have a probability of 0.5. And that's the only case in which you would expect something that looks somewhat symmetric. There's no obvious floor or ceiling effects in that case. So this is another instance in which there aren't separate pieces of information that you would need to know to be able to describe the distribution, the width, variance, because it's determined by the mean, and also skewness. Thank you. Yeah. It restarted. Can I just pretend like it was like, oh, like you made a great point? Because it's timed well, you got to work with that. Here's one that's also discrete that is specifically for counts. It's called Poisson. All I know about that word is that it's French for fish.
Okay.
I'm told. I speak Spanish, but not French, but that's what I've heard. This one is often used to characterize count data because the lowest it can be is it approaches 0, but it never goes below it, and it goes into positive infinity. And a consequence of having a low mean is skewness. So for instance, in this case, this is another one where the mean and the variance are related to each other, In this case, the mean and the variance are supposed to be the same number. So the yellow dots is what this would look like if the average count was 1, like number of cigarettes smoked or something. Then the variance is also supposed to be 1, and most of the data would be shoved over here on the low end. Very few cases would be expected to have a count above 5 or so. Purple is 4, a mean of 4. It starts to look a little more symmetric, but there's still somewhat of a tail hanging out on the right side. And 10 is the one where it starts to look symmetric. Note the reason that these are dots is because it's not possible in this distribution to have values in between. Either you smoked 11 cigarettes or 12, but it's not 11 and a half. Once you light up, it's a cigarette. All right, Zoomers, any questions on the Zoom front? Any questions in front of me? No, we're good? Do you like pictures?
Yeah, I love pictures.
Yeah, I like pictures, yeah. All of these...
We don't need to remember these formulas.
Oh, hell no.
Okay.
No. Oh, no, gun to my head, I couldn't tell you any of these off the top of my head. The only one that I think I know off the top of my head is this one, because it's the probability of a 1 if that's what you got, times the probability of a 0 if that's what you got. The end. No. My point is that these are variables that have, these are like shapes of variables that you would see like out in the wild, like in real data. And these are the formulas by which, if the variable follows that distribution, it tells you what the mean, the variance, and the skewness are supposed to be. I just want to give you a sense of what kinds of variables you'd be working with in quantitative data. That's all. Just pictures.
Is there another term that you could use instead of skewedness? The formula looks familiar, but I don't remember it being called that.
Asymmetry?
Okay.
Anyone help?
We'll go with skewedness sometime.
Shoved overness?
Okay.
Yeah, I'm going to start going with made-up words. Here's another one. So this is a special type of count. This is what I refer to as an if and how much variable. We talked about this a little bit last week. It results when you're mixing two different types of populations, one in which a phenomenon simply doesn't happen, and one in which it does to some extent. So I call it if and how much. And this is an overlay of real data here. So the bars show actual observations, and this is sort of this is a histogram that shows how many are in each of these categories here, artificially grouped together. And each of these lines is the fit to some sort of distribution. And the point that they're making here is that the number of people who said 0 is far more than would be expected in either this Poisson distribution or its stretchier cousin, which is called negative binomial. But there are distributions that have extra zeros in them for this type of data. So there's a lot of variables that take this form. When it's an outcome, we can use these sorts of distributions to predict it. When it's a predictor, we would want to pay attention to the idea that we have an if potential variable lurking in there as well as a how much variable for the quantitative part. So yeah, I just wanted to show you pictures. That's it. The reason I wanted to do that is because everything after this is going to be based on only one picture. Because that's the one that allows simple hand calculations. That's why it starts there. But the rest of the world is out there for you. Yeah. So showing pictures, all of these previous plots show discrete distributions where the values are integers or categories and there's nothing in between. In that case, the type of plot that you would typically make is what's known as a frequency plot, where you simply show the number of cases in each category. There's no rounding or smushing or finagling. If you have a variable that's truly continuous, something like heart rate, I'm trying to think of other ones that would come out of some sort of response time. Things where you're measuring it to some sort of level of precision. In order to make a picture like that, you have to create some sort of artificial grouping to show how many are in each level, where level is something you define. And those types of pictures are called histograms. I'll show you how to make those because they're very helpful for just understanding what the shape of a variable. And you would need to choose how many of these rounding points, known as bins, would be helpful. So this is the rest of your life for this semester. This is our friend, the normal distribution. It's continuous, which means two things. It means that it goes on forever and ever and ever in both directions without end, and that it takes in between values. So the probability of any one exact value is undefined because there's infinitely many of them. You could keep chopping it up into finer and finer gradations. So people typically talk about sort of the probability or the likelihood after this point or before this point. This formula actually is one of the harder ones. Gun to my head, I could not recreate this, even though I do this for a living. So you can believe me when you don't have to memorize this stuff. It looks really familiar to me at this point, but I'm not sure that I could recreate it perfectly off the top of my head. But what I want you to know is that this shape is created by two pieces of information, and they're separate. Unlike any of the other pictures where the mean and variance were yoked together, this is one of the few where they're actually two separate pieces of information. So introducing some vocabulary, and by vocabulary I mean notation, ways of writing about these things that are somewhat universal. The mean is almost always written with this U-looking thing here. That's mu. Incidentally, do you guys know how to do equation letters in like PowerPoint and Word and stuff? You do?
Yeah,
You had to for what?
our last class.
Yeah, we're in the same class together, so yeah.
Which class was it?
I'll try the stats.
41, 43, that one, or a different one?
41, 43.
Okay, cool. Yeah, well, that's a useful skill. Let me just show you real quick for those of you who don't, because hunting and pecking for special symbols is really annoying. So I'm just going to pull up a Word document. All Office products do this. I'm guessing the Mac versions and OpenOffice have this too. If you hit Alt and then the equal sign, a box pops up like this. Yeah, Alt equal sign. Inside the box, type equation here. My computer's angry with me because I'm like doing too much with it at a time. Oh, wait, question? I have a question
No,
here.
aha moment.
Can you all see the screen? No. Did it stop sharing? It should be here. You can see it. Okay, good. Thank you. Type equation here. Come on. No, more chats? I can see it. That was earlier. Okay, cool. All right, we got it. Come on. Let me type it. You're ruining my demo here, Word. Okay, there. All right, now it'll let me. So here's the trick with writing Greek letters. If you start with the slash that's above the enter key, which one is that? Backslash? Forward? I don't know. It's the one above the enter key. And then you write the name of the letter you want, like mu, and then you hit the space bar, it jumps into the character. Oh, see, you didn't know this. Yeah, so cool. Yeah. So that's way easier than hunting and pecking. So yeah, I'll do it again. Ready? Space, or excuse me, slash, mu, and then space, and it jumps in. Now, if I want to add subscripts, like we're going to have subscripts that say whether or not it's a variable or a constant. If it's a variable, it's going to get an I for individual specific. That is shift and then underscore, the one next to 0. If you do that and hit an I and then hit a space bar, it jumps in. If you want to do a squared term, so like if I have my mu here and I want to do squared, that is the hat thingy above the 6. Caret, is that what that's called? It's a hat in stats notation. And I do a 2, and I hit the space, and it jumps in. So if you're writing equations ever in a manuscript, these look a lot better than trying to do it just in the regular text. So that's where I did all of mine, just as an FYI.
Well, what do they use to get the I again?
The I one is, let me back up. Yep, so here's my mu. It is shift and the underscore key that's to the right of the 0. That gives you, that means subscript. And then whatever letter you want for your subscript, you can have 2 of them if you want. And then you hit space or enter and they jump into subscript forms. Yeah. So that's how I did all that stuff relatively quickly. So this is mu. U-looking thing is how I will refer to it because it looks like a U to me, but it's mu. That means the mean. Something special about the normal distribution is that if your data actually follow this distribution, the mean, the median, and the mode are all the same number. The arithmetic mean is the same thing as the median, middle value is the same thing as the most likely value, which in this case means the one that's the tallest. So for instance, if I look at the blue line, the red line, and the orange line, all of them have the same mean of 0. If I know nothing else about a set of data, and I want to make the best guess for what this outcome value should be for any person, it's the mean. So I would make the same guess if I were guessing for the blue distribution as for the red as for the orange. But those aren't the same, clearly. It's much more likely, much taller, to be a mean of 0 in the blue because of the other thing that characterizes this distribution as a separate estimated concept, which is variance, or standard deviation, its square root. So the difference between blue and red and orange is that blue has variance, that's this thing here, sigma squared. So variance is the squared version. The square root is standard deviation. It has a variance of 2, whereas the red line has, or excuse me, 0.2. Yeah, and the decimals matter. Commas matter and decimals matter. The red line has a variance of 1, and the orange line has a variance of 5. So this is the width of the distribution. If I'm trying to predict for the orange people here, I can say that the most likely value is 0, but it's not all that much more likelier than any of the others. So we really have to know 2 things to think about how to make predictions here. If your data follow the normal, there's not supposed to be any skewness. It's supposed to be symmetric. Not supposed to be any kurtosis either as a function of that. The opposite of that, these are distributions that maybe you thought might be normal because it's a score that could go forever, but they're not. Question in the back.
So on slide number 12,
Yep.
the tallest one being the most likely, would it be fair to jump ahead and associate the smallest variance with the highest likelihood?
Yes.
Okay. 'Cause I was like, okay, I just want to make sure I wasn't thinking out of
The certainty with which you could say the mean is the best guess is related to how less or few variance, that's not right, the right English, how small the variance around it is. Right, like the most certain scenario would be everybody gets a 0, right? That's called a degenerate distribution, actually, that's a thing. The more they spread out from 0, the less certain you can be that any one person would get a 0 as your best answer. So yes, you can make that, and that's actually foreshadowing the second half of this. So thank you.
Would that be magnitude then of variance?
Yeah.
Okay, got
The
it.
bigger the variance, the less certain you would be that the mean is like the highest.
Okay.
Yeah, it's the relative. Like blue, it's like yes, it's 0. I don't need to phone a friend or anything. It's 0. I got this. And orange, it's like 0, because orange is very wide. It has a lot of variance. So, other questions, thoughts? So yeah, this is skewness. So in this case, I would wager that they have some sort of instrument where there's only 25 possible, and the worst you could do is nothing. So the distribution on the left here is what's known as negatively skewed. It's where the tail is going. So it's backwards from how you would think about it. It's where the information isn't is the direction of the skewness. So this would be like a ceiling effect on the left here. The right would be known as a floor effect. The consequences of this, if these variables are outcomes, you would have to make sure that you can find a model that understands that the highest possible value the model should predict is 25, and the lowest possible value that it should predict is 0. The normal distribution doesn't understand that. So variables that look like this would probably not be good candidates for that type of distribution unless you can do a really great job in predicting why it is that you have these boundaries. And there's a special word that if these two figures were combined, if you had a pile of people who were really low and a pile of people who were really high, yeah, two humps, there's a word that goes with it. By,
I want to say binomial, but I'm wrong.
very close, by something. That very would mean two variables. It's bi, starts with an m after that.
Bimodal.
There you go.
Yep.
Bimodal, meaning two modes, two most likely centers, yeah. Those can show up if you have a really, really strong group effect in your design. Like if you have two groups of people who are really different from each other, then you have a distribution around one type of person and a different distribution around the other. Okay. Questions, thoughts? Yeah, vocabulary. All right. So how do we find this stuff? In the case of the normal, you can use very straightforward math to figure this out. And so this is the kind of stuff I'm guessing you've seen before. Even if you've never taken statistics, you know how to calculate a mean. What I want you to start getting used to is seeing the notation with which this is described more generally, because this is a system of language. And it's one of those things that if it's foreign to you, it's real easy to be like, stop it. But you know what this is. This is a mean. So here's some new notation here. This right here, y sub I, is how I would talk about that. Sub meaning subscript. That is how we'll indicate an outcome, one outcome variable, one column in a data set that varies across individuals. I is a common subscript to differentiate among cases in a sample because individuals could be anything. Individual people, individual schools, individual rats, individual countries, whatever your unit of analysis is. Individual covers it pretty well. Italicized big N is the number of people in your sample, total sample size. Y with a subscript of the big N, Y sub N is how I would talk about that, refers to the last person in the sample. So in writing these things out, we want to be able to abbreviate across our cases. If we numbered our cases, it starts at 1 and it ends at N. The last one here, Y with a line over it, is known as Y bar. And that's supposed to be how we represent the mean of a specific sample, arithmetic mean. And note here that just like N doesn't have an I, and Y bar doesn't have an I, because those are constants. Those are one number that holds across everybody. If I have a sample of people, N characterizes the size of the sample for everyone. If I have a mean of a sample of Y bar, it characterizes the mean for everyone. So putting it together, the mean of the sample is the sum of all the observations, starting at person 1, going to person N, divided by the sample size. This, written more quickly, is this thing right here. Have you seen this thing before?
Sum.
Yeah, sum, or capital sigma. Yep, that means sum over. So this right here means sum over y sub I, starting at I equals 1 all the way up to N, and then divided by N. So it's the average value across all of these observations, equally weighting everything. Next one, variance. So the idea of width of the distribution, the amount of dispersion. The way that variance is typically abbreviated in a sample is S squared. In a population, it's sigma squared. So this thing back here, that's a lowercase sigma squared. That usually is referring to like the population variance, whereas mu is the population mean. In a sample, we substitute mu with y bar, which is the sample mean and then the sample variance. And variance is calculated like this. It's how far off your observation is relative to the mean. So you would expect, because the mean is supposed to be the middle, right? Some people are above it, some people are below it. If I summed those deviations that are both positive and negative, they would work out to be 0, and that would not help me. So to counteract the direction, we square the deviations. You could, in theory, take the absolute value, but it works out that mathematically that's a way harder thing to work with, and so they square it instead. So how far off is the mean from your observation squared, sum that over people, and then divide by n minus 1. So why is it minus 1? That's taking an explicit acknowledgement that there's no way we could have done this without already knowing what y bar is. So in terms of unique pieces of information about our sample, we know that we have n data points in a variable. That means that we have up to n ways to try and summarize all that information in the variable. Rather than calculating the mean and the variance and all that stuff, I could be like, well, I'm going to have my parameter and the me parameter, and it says what my score is, and the u parameter, and the u parameter, and you, 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 and everything, right? All the way up to n. That would be just as useful in terms of capturing the information, but it wouldn't do any good in terms of prediction. But that's the limit of what we could do to make sure that we capture all the information is n parameters, one for each of us. So how many we spend, then, we keep track of. Because in order to make a prediction for each person, at this point we're just predicting the mean, we spent 1. If I had a mean for group A and a mean for group B, and so then I deviated each of these from the group means, I would have spent 2. This number goes to 2. So more generally, this term on the bottom is what's known as denominator degrees of freedom. It's because it's in the denominator, but degrees of freedom means how many things have you spent to be able to characterize a variable, and how many are left over. Left over is what the n minus 1 becomes right here. So the formula by which people calculate dispersion is variance, but the way that's more intuitive to talk about it is the square root. I'm saying root because I don't want to make people angry, but can I get a show of hands? How many of you are native Midwesterners? How many are not native Midwesterners? Okay, so for the rest of you, I'm saying root. For those of you who are native Midwesterners, I would say root. Root. I know. That sounds perfectly acceptable to me. I go up on the roof, I drink root beer, and I calculate square roots. It's all fine. To other people, they're like, and I didn't even know that was a thing until I was like an adult and talked to people who weren't from the Midwest and learned that it was root, or it just sounds weird. So I'm trying to train myself to say root, but if I get a little too tired, if the baby bottle of Diet Mountain Dew dries up, then I may switch back to root, and you'll have my apologies. But this idea here, how far off on average, that's standard deviation. So I know that if my mean is, let's say 10, and the standard deviation is 2, then on average, each person relative to the mean is off by 2, either minus or positive. That's a useful thing to know. So putting it all together then, the mean in APA style is often abbreviated with just a capital M. So when you describe a variable in parentheses, if you give descriptive statistics, you would say M equals a lot of the time. That's central tendency. If we're trying to talk about the mean for the big picture population, that's mu. What we're using to approximate it with our own data in the sample is y bar. Variance then, squared dispersion, is how far off squared each observation is from the mean. The square root of that is standard deviation, and so that's the average deviation. One other thing that occasionally shows up is this thing called coefficient of variation, which is a ratio of the two. I don't know why that's useful, but it's a thing, so I'm just putting it in here. Questions? All right. If you wanted to calculate skewness, it works the same way, except rather than having to square it, you cube it. That's related to the idea that this is the third moment of the normal distribution. So these are differences then in terms of how the mean, median, mode shake out under skewness. So in situations in which you have a positive skew, something like the median home price, right? What's the cheapest in theory that a home could be? there's some lower bound, right? It's somewhere like 0 in theory, but maybe not even a tiny house would be 0. But you can't have negative home prices, right? Now, what's the upper end of home prices?
500,000.
And then limited, right?
Yeah.
It depends. Are you the football coach? Are you a professor, right? Are you the provost or a grad student, right? It's what high is sort of a sliding scale, but in theory, there's no upper limit. So oftentimes when you talk about home prices, they don't report the mean home price, they report the median. Because in a distribution that's positively skewed, where most of the people have reasonably priced houses, the mean will be closer to where the bulk of the data is than the mean. The median will, excuse me. Yeah, I need to refuel here. The median will be closer to the bulk of the data than the mean, and the mode will be even closer than that. If you have a distribution that's truly symmetric or symmetrical, that sounds weird to me, but I took this from the book, and he says symmetrical, so be it. These 3 things are right on top of each other, and then the opposite pattern happens in case of negative skew. So when your data aren't symmetric, that's when what you report matters. There's nothing that stops you from reporting more than one thing, but most of what we do in statistics is built on trying to recapture a mean rather than either of the other 2. So that shows up most often in terms of inference, even though you have these options for descriptive statistics. Here's kurtosis, and kurtosis comes in 2 forms. There is flatter than normal or wider than normal, and this is the one that's almost impossible to tell from variance. It's not something that you would ever do anything with in terms of the information in practice. It's supposed to be normal, a 0 in the normal distribution, but otherwise doesn't really matter. So there, we've covered it. So if you have a skewed variable, things that you would also want to report besides mean and variance, median, and potentially percentiles. So the definition of a percentile, it's the value at which that percent of the data is less than or equal to. So if I say that you're at the 45th percent, then that means that 45% of the data are at or below that value. So you see percentiles a lot in terms of trying to interpret test scores. Like, where did your child fall? Like, mommy, I got a 6. And you're like, good? Or, I'm sorry, I don't know what 6 means. But then if you get, oh, the 6 is in the 95th percentile. Well, yay for you, right? Now I have a meaning of it. And so percentiles are used to try and give some sort of normative reference information. They're also used to try and deal with unwieldy data in terms of things that are highly skewed, have extreme values, or both. And so in those sorts of cases, people might report the median, which is the definition of that is the 50th percentile, interquartile range, which is the difference between 25th and 75th, and then minimum and max is always useful to report, no matter what. The range is always something that you would have. Pictures like this occasionally show up. This is what's known as a box plot. There are cooler things than this nowadays. I once had a reviewer recently ask for something called a violin plot. And I was like, what the hell is that? And I asked the Google, what is a violin plot? And sure enough, they pop out. They're more colorful and they have like shapes and stuff in them. They're cooler, but it's sort of the same idea. It's trying to show you visually not just what's the mean, what's the variance, but sort of where is all the actual information around that. After a certain point of extreme value, you're known as an outlier. These would be not the good kind like Malcolm Gladwell outliers, but this is like the, why are you telling me something that's so different from everyone else? And there's a whole set of literature on how to handle or deal with outliers or get rid of them. Don't. Data aren't fish, they don't need to be cleaned. If you have concerns about outliers, there's models for that instead. So this is something that an outlier is in the eye of the beholder. A lot of things go into whether or not the values would be believable, and if they are, whether or not they would be having undue influence on the rest of what you're doing. And we'll talk more about that later. Okay, so how are we doing so far? Yeah, so I'm taking most of this is not new so far. No one's willing to say that? Ish. Heard it before, it's been a while.
There's some cool tips in what you're saying.
Cool tips? Okay, such as?
the one with the text box or the math box, that was awesome. And then I
Oh,
started playing with my pen. It's even cooler.
and it's even cooler. Well, I'm glad. Yeah, tech tips, excuse me, are always good. So now it starts to get a little bit more esoteric. Sampling distributions. So we tried to hint at this idea on this slide here. The question in the back, like, is it related to variance? How certain I can say this is the mean and this is the expected value? Yes. In addition to just knowing what the mean and the variance of a variable are, we also want to know how precise those estimates are. So if I were trying to take a sample and make some sort of conclusion about my sample relative to what's supposed to happen, and I grab 2 people, and I take the mean across 2 people, intuitively, how much stock do you put in that number? A mean across 2 people? 3 people? Somewhere between and okay, right? That's what we're looking for. Generally speaking, more people, more information. More people is better. We'll talk about statistical power in maybe 2 weeks or so. One of the things that when you're planning a quantitative data analytic project to do a research study, you'll have to be responsible for estimates of power, meaning basically how many people do I need to collect? And this is a very, very common thing that I get asked. And do you know what my answer is? The answer is more. Always, you need more. Some of you who work with very large secondary data sets, anybody do that? No? Not yet? Not yet? Well, if you were to, then you actually have the opposite problem. You have so many people that everything looks like it matters, and trying to sort of the wheat from the chaff can be a problem in the opposite regard. But most people that I work with, they're struggling to get real subjects in their studies because subjects are hard to come by. So you want to make sure that you have enough people to where you can say that, no, this is a good estimate, I believe it, and trying to figure out how believable your estimates are. That's what this is about, sampling distributions of the statistics. So is it really the mean? Like it's the mean, or is it mean, question mark? That's the question. There are 2 general ways that we can find the answer to that question. The one that we're going to do in this class, due to lack of time to do anything else, is to focus on what's known as asymptotic sampling distributions. These are formulas. If things are true, these formulas hold. That's basically the gist of it. The majority of quantitative methods still relies on these sorts of approaches. Nowadays, there are different approaches that are known as approximations through resampling. Those of you in 4143, if you took it with Brandon, I think he does some of this kind of stuff. If you took it with someone else, maybe not, I'm not sure. But these words that you may have heard of, bootstrapping, jackknifing, permutation tests, Markov chain, Monte Carlo, all of those are ways of resampling from data to try and figure out what the sampling distribution looks like. So if I have my data set, for instance, jackknifing, and I take one person out and I get the mean. And I do it again, and I take a different person out and I get the mean. Take another person out and I get the mean. How different are those numbers? That's a way to try and approximate how good of a mean it is. If the mean changes a lot when you take one person out, that's not good. That's not a very stable number. So chapter 18 of your textbook has a whole bunch of stuff about this. I would refer you to that as sort of an introductory treatment of these techniques. They become more important whenever you can't rely on off-the-shelf formulas. So when you're in a situation where you're trying a new model or a new something to where they haven't done the proofs necessary to give you the formulas, or the formulas are just not possible. That's when these sorts of things are more useful. But we're starting with the first one here in the interest of time. So building intuitions then about what affects this process. So one of the things that I like to do to try and convey things as well as to make sure that I can understand what I'm talking about is something called simulation. So I make up data. Did you know that when you make up data, people are really cooperative? the fake cases in the data set follow whatever distribution I assign them to. It's magic. It's one of those things that makes you feel all powerful, right? A lot of the research that happens for people who specialize in quantitative methods like myself is what's known as simulation research. The idea is that you're trying to see whether or not something that is known to be true holds all the time. So for instance, this normal distribution, let me go back a few slides. If you have a test that's designed for data that look like this, and your data looks like this, you trust it? Empirical question, right? That's the idea behind quantitative simulation research is you make up fake data where you know what the answer is. And then you do whatever analysis you're not sure about and see if you get the right answer back. And oftentimes the problems that I'm interested in are related to small samples. If you can't do something the most right way, what is the least wrong way? That's the typical type of research that I'm interested in. But the basis of that research is right here, the idea of simulation. You can make up data where you know what happens to demonstrate what should happen or to see if the techniques that you're using give you back the right information. So the code that I use to do this is actually on the next slide. This is just for your reference, in case any of you feel like this is cool and you want to play with it. It's SAS code. SAS has random number generators that follow all kinds of distributions. So I made this up. This variable is called y. I told it, in this variable, I would like 1,000 fake people. I would like this variable to have a mean of 0, and I would like it to have a standard deviation of 5. So on average, I want each case to be off from the mean by 5. That sentence, written in notation, looks like this right here. Y sub I, meaning each person, the squiggle, that's tilde, means distributed as. And then capital N, which I know I just told you is sample size, it's now normal. Sorry, I only have 26 letters to work with. We have to reuse some of them sometimes. I italicize sample size, I try not to for normal. And then in parentheses, the two pieces of information you have to know to be able to say what the normal distribution would predict for each data point. Mean, and the second one, depending on who you read, is either going to be standard deviation, that's sigma, or standard deviation squared, which is variance. It's one of the two. In this case, I'm using sigma. And so what should have happened is covered by the blue line over this histogram here. And what actually happened is the red line. With 1,000 people, I pretty much got it back. 1,000 people, in this case, looks like it's enough to be able to say, yes, this sample is smack dab on the population. So what would impact then how close the mean for the sample is to the mean that I told it to be in my simulation, the truth? Well, let's look. Top picture on the left here, simulating 10 observations, supposed to have a mean of 0, works out that the actual mean for the sample, y bar, is 0.84. Off by like 1/5 of a standard deviation. 30 people, the mean is closer to 0, but still not there. 50 people gets even closer, 100 people gets even closer. So this is what we talked about earlier. The more people you have, then the closer your sample mean should be to the population mean. More people are better. The other thing that affects it is the variability around the mean. So in this case, we have 100 people in each picture, standard deviation of 5 versus a standard deviation of 8. In each picture, the blue line is truth and the red line is what I got back. So there's a bigger difference between the two lines when I have more variability. It's harder to nail down what the mean should be when there's more noise around it. In pictures, just to demonstrate that point, I have a relatively small standard deviation of 3 in the first picture, growing to 5 over here, growing to 7, and growing to 9. And the mean's supposed to be 0 in each case. Now these are only one-shot estimates at each sample size, but if I did this over and over and over again, these tendencies would come out. There would be more wiggle room around what the mean should be when there's more variance. It'll be harder to nail it down in any one sample because there's more noise around it. So the best case scenario would be I have a lot of people and I have very little information that's around the mean. Everybody's sort of clustered in the middle. Then I would have the best chance at saying, yes, this is the mean, it's a great estimate of the population. Okay. With me? Okay. So that's building up to a concept that is somewhat tricky to understand at first, even for me. The idea that the mean has a variance. Not the mean and the variance. The mean itself has a variance. So this thing right here, what I'm trying to say is that the sampling distribution of the mean, so this is the mean for sample S. So if I did the same study over and over and over again, each study, mean for study 1, mean for study 2, mean for study 3. What this is trying to do is describe the range of values that those means would take. That range of sample mean values is supposed to be normal with a middle point near wherever the population would be. If I take the same type of sample over and over and over again, I hope that I'm closing in on what the population should be. The second one, this is like standard deviation, but instead of talking about the average offness of a person to the mean, this is talking about the average offness of a sample mean to the population mean. And that is given by our sample variance divided by the square root of sample size. So the variance of the mean is the variance of the sample over the square root of n. Blech. That term right here, to avoid confusion, gets a specific name. It's the standard error. Not standard deviation, standard error. Error and deviation sort of mean the same thing. They both are offnesses, but what it's off from is different. So standard errors go with statistics. Like the mean is a summary of my information from my sample. I want to know how wiggly that mean would be across samples done over and over and over again. Wiggliness is conveyed by standard error. And as we just saw, how do you get your standard error to be smaller? Well, less variance, right? Less noise around the mean, and more people. More people, less variance, less wiggle across your sample means. Now, this thing right here, you'll note this is sigma in the notation for a reason. The best version of the standard error that we would come up with is if we know the population's variance. To that I say, well, duh. If I knew what it was, why would I be doing research on it? There are a few cases in which you would have access to a number like that. For instance, if you have a standardized test where all this research has gone into developing this test and they have normed it, so to speak. They have a scoring system by which you're supposed to have a mean of 100 and a population variance of like 10 or something, right? 15 would be something like that. Like if you trust those numbers, you might be able to use those numbers. Other instances in which you could trust the population variance is if you don't need one. Like for a binary variable. In that case, the variance comes from the mean directly. That's not a separate number that we have to go and find. But other than those two situations, we just say, yeah, I know we don't have that number, so we're just going to use one from our sample. And that's sort of like cheating to me. It's like, no, wait a minute. How do I know how wiggly my mean is? Well, it depends on the variability in my sample. But I only know about my one sample. I want to know about wiggliness across all the samples. And I'm only using one sample to tell me how all the samples would be? Yes. That's statistics. You gotta have faith. So this concept is a little bit tricky. I have an example for it queued with Mountain Dew, but that'll take longer than we have, so I think this might be a good place to pause, review, and ask questions. Okay, so what did we do today? I'm going to minimize that, put up my zoomers as well. You guys are on the hook for this as well. What did we do today? Yeah, like what? Which kind? Yeah, our new friend normal.
Skewed.
Yeah, distributions can be skewed. So properties of distributions, properties of variables, right? Skewness is one. Shoved overness, as it were, asymmetry. Terms that would describe how dispersed it is.
Magnitude of variance.
Variance and its friend.
Standard deviation.
How are they related?
Squared.
Which one's squared?
The
Variance is
No,
is-
variance is
variance is
standard
the
deviation
square.
is squared, right?
Standard deviation is the square root of variance.
Okay.
Variance is standard deviation squared.
Yeah.
Yes, so standard deviation is average offness from the mean of any case. Variance is average squared offness. Yes. How about middle? Things that go in the middle.
Mean.
Mean, two more, starts with M.
Mean.
Median mode. When does it matter which one you report? But usually we do the mean, but when does it matter?
When it's
Median matters when it's
Yeah.
skewed.
Shoved overness. Yes.
median.
If your data have some sort of skewness, they won't be right on top of each other. If it's symmetric, they should be. Yes. Let's see. That's good. That's a lot of stuff. And then we start talking about sampling distributions, and that's where we'll pick up next time. The idea that I want to know, yes, 10 is the mean. Final answer. Or 10 is the mean. Those ideas, that's what the sampling distribution is trying to convey. The precision with which we believe in our estimates. And that precision is higher when we have more people and less variance. There we go. Got it. Questions?
I was just curious when the first assignment next week will be open.
I think I will have it open by Thursday. Yes, so that will give you about a week and a half. And you've already actually started working on it if you've already started getting into virtual desktop, because I tell you that will be the hardest part of it. I guarantee it. Other questions? All right, then cheers. Go have a good afternoon, and I hope to see you all Thursday. Yes, learn about the distribution of data and what that means. Indeed, we're going to pick up there next time.
Okay, I can get to the virtual desktop, but I am still struggling to find